In this lesson, we'll be looking at practical interpretations of the definite integral. So remember that when we talked about Leibniz notation for a derivative, we talked about how we could figure out the units and look at how these units fit together, because it looked like a quotient. But if we look at the full integral notation, remember that we always have f of x times dx. And so this is a product of the units for the function and the units for the variable, every single time. So let's just think about that for a moment. Let's suppose that x and f of x had the same units, even though this is not exactly common. You would say maybe centimeters times centimeters would give you centimeters squared, which we know that's an area unit. And so it would make sense to say, hey, this actually is an area. But let's take a look at some further ideas here. Let's suppose that we have a velocity function in meters per second, and t is a time in seconds. Now, one of the things we talked about before was the area under the curve is equal to the distance traveled. And so let's see if that makes sense when we play around with the unit. F of t has meters per second as the unit, and dt is seconds for my units of t. We get meters for this. Meters are a unit for distance. So now let's take a look at this next example. We've got a projected cost per day to heat our home in dollars per day. We'll look at the time and day since December 1st, 2016, and we want to interpret this integral. So let's first just take a look at the units. We'll see if t is in dollars per day, and remember we would just multiply, t is in days. The total cost here is in dollars, which should make sense. With that said, what does this represent? Remember, if we're looking at sort of a rate of change and we integrate it, we were given some sort of value out of this. That value is actually a total change. So here's what we get. This represents the total cost to heat from December 1st to February 28th, which is exactly 90 days later. So now let's formally state this fact that we're going to be using. If your function is a rate of change, then the integral, this area under the curve, actually represents the total change in that quantity in which the function is a rate of change in the quantity. So when we say total change, we mean basically a difference between the starting value and the ending value, between t equals a and t equals b. Let's take a look at an example here. We've got a bacteria colony that initially starts with 10 million bacteria, and we're given a rate of change of 1.74 to the t million bacteria per hour. What we want to know is what the total change in the bacteria population is from 0 to 2, and then we'll turn around and find what the population is actually at t equals 2. Here's the integral that represents the total change. We're going to take the integral from 0 to 2 of the given function, 1.74 to the t, dt. And again, this represents the total change in the bacteria population. Now you'll need to use your calculator in order to do this, so feel free to pause the video and give it a try. I get approximately 3.66, and remember our units are million bacteria. And this is the total change from 0 to 2. Now let's take a look at the population at the time t equals 2. This is where we actually need to pay attention to the overall picture. So while the integral tells us the total change, in order to find the actual value, we need to take a starting value, which is actually this 10 here, and add on the total change. To find the population at t equals 2, we take the 10 million bacteria we started with, plus the 3.66 million bacteria that accumulated between 0 and 2, and we get 13.66 million bacteria. We've got a man who starts 50 miles away from his home, and he takes a trip in his car. So what we're looking at is a graph of his velocity. We're going to assume that he's driving on a straight road, and his home lies on that straight road. At the beginning, the man is starting 50 miles away from home. And then this velocity represents when he is driving towards his home. And this velocity represents when he's driving away from his home. What we want to figure out is when is he closest and approximately how far away is he when he's closest. So this is kind of what we were talking about in the previous chapter when we were talking about taking a derivative and reversing the process. Let's start out by highlighting here this t-axis. When we cross this t-axis, this means that the car has temporarily stopped moving. So you'll notice during the interval from 0 to 2, the car's velocity is heading towards the house. But then from 2 and onward, the velocity is below the t-axis, meaning he's traveling away from his house. So as of 2, he got as close as he possibly could. And you could also look at this as the fact that this would be a maximum, or in this case a minimum for our distance from the house. With that said, when is the man closest to his home? He is closest at t equals 2. At t equals 2, he has reached as close as he could possibly be. And now the question is asking, how far away is he at this point? What we need to remember is that the integral is the total change, but the integral is also the area under the curve. What we need to do is we need to figure out roughly what is the value of this area right here. Now I have one method and Wileyplus has a different method. I prefer to use geometry to try to find a shape that matches up with this as best as I can, but Wileyplus uses more of a box counting method. So we could try both for my purposes. Here's my method. I would say a triangle that has roughly the same area might look something like this. This triangle goes up to about maybe 35 miles per hour, and it has a width of 2 hours. What I'll do is I'll claim the area from 0 to 2, and I'm going to say the area of the triangle is 1/2, base is 2, and we'll say the height is 35. So we'll claim he went 35 miles. Remember, this 35 miles, this area under the curve if you will, represents the distance that he traveled back towards his house. Now this is where we need to go back to the introductory piece of information. He started 50 miles away from his house, and he traveled 35 miles back towards it. Approximately how far away? His distance from home at 2 hours would be 50 miles away, minus the 35 miles he drove towards his home, which is now 15 miles away from his house. Next we want to figure out when is he farthest from his home. This is the idea that he's going to be driving away from his home, and driving away, and clearly this region's larger than the one that I found earlier. He's going to be driving away, and at 5, he stops driving away from his home. So 5 must be the time when he's farthest away. With that said, to find the distance he is from his house at that point, we'll again need to calculate the area under the curve. I'm going to draw my triangle something like this. Maybe I should go a little bit below the 60 mark and say maybe 65 or something for the height. If we take this area from 2 to 5, I'll say 1/2, the base is 3, and we'll say the height is 65, keeping in mind this is a distance away from his home. And when I do that, I get about 97.5 miles. So again, that area represents how far he drove away from his home. He started at 15 miles away at the 2-hour mark, and we know that the change from the 2-hour mark to the 5-hour mark is 97.5 miles, so we're going to add these two values together to get 112.5 miles away. Let's look at one more example. We've got two species of plants, and we're going to look at the rates of growth of their populations, measured in new plants per year. At first, we'll assume that the population of the species are equal, which is important in order to make any conclusions. Over the first year, the growth of species 2 was not quite as fast as the growth of species 1, but at 1 year, their growth rate was the same. However, what we want to know is which population is larger. So we look at the rates here. And what you'll see that you've got this region above the axis for species 1. And the area for species 1 is larger than the area for species 2. What that means is that the total change in plants for species 1 was higher than the total change in plants for species 2. Species 1 has a larger population after 1 year since it has a larger area. What about after 2 years? What we're going to be doing is comparing the area under species 1, as you can see, to the area under species 2. Now, it might not be completely clear which one has the larger area, so this is the tip that I would give you. This region is the region of how many new plant species 1 got during the first year. This region is the number of new plant species 2 got over species 1 in the second year. But then you've got this little common region, and you don't really have to pay much attention to this common region as far as making your comparisons. But what you can see is this region is definitely larger than this region. So the number of plants that species 1 gained over species 2 in the first year was much beaten by the number of plants that species 2 gained on species 1 during the second year. Species 2 has a larger population after 2 years since it has a larger area. So then the second example is going to ask us, how much does the population of species 1 increase during the first 2 years? What we're asked to do is try to come up with approximately how much growth has happened on species 1. And again, the change in population is equal to the area under the curve. So let me show you the Wileyplus method for this one. What we want to do is we want to figure out what the area under the curve is for species 1. Wileyplus does a bit of a rough measurement of about how many boxes total are being made up by the area under the curve. We can start out by counting them like this. 1, 2, 3, 4, 5, 6, 7, 8. I'd say these make about a 9th box, and maybe a 10th box and an 11th box. And then you've got 12. And we'll say this is about 13 that's going above. 14, 15, maybe 16 here, and 16 and a half. 16 and a half boxes is what we're looking at. But I need to convert these boxes to an area. So we need to figure out what the size of each box is. Well, a box has width 1/4 and height looks like about 750. So let's say 16.5 times 1/4 times 750 will give me the total area under the curve, and this is the total number of new plants per year. I'll go ahead and round to 3,094 new plants will be my approximation for what I get here.